We're doing Pie method. We're doing Pie method. Sure. So Pie method, it's either we're calculating the sending end voltage or sending end current. Sending end voltage or receiving end voltage with their currents. So it's either you're looking for input information or output information. To go about this, for this specific video, I'm only going to take you through how to come up with your formulas to find the sending end voltage. To start, you need to find, these are the steps. So typically this calculation, they give you information. This side, your impedances, they give you information for your impedances, and so as you apply the calculation, you're moving backwards. So here's the idea. Step number 1, you need to find VR phase. So our VR phase is the same as V phase at the angle of 0 volts. So V phase, these calculations are star connected. So to find your V phase, you'll say V phase equals to VL over root 3. 2, you need to find your IR. Our IR is the same as I phase at the angle of theta, the given angle for theta. So because it's star, we said I phase is the same as IL. So in regards to IR, you need to find IL. To find your IL, you're saying P over root 3 VL cos theta if they happen to give you a power. If they give you apparent power, you're saying S over root 3 VL. I am flowing, my friends. So all this information is based on given data. They'll tell you it has been delivered. It delivers an output or a voltage of the line given voltage at the receiving end. IR, you'll always have to find it. Next step, you need to find the impedance between points A and B, between these points. So to find that impedance, as you can see, between A and B, you have a resistance plus a inductive reactance. So you just need to find your inductive reactance if it's not given. We know these formulas for reactances. Step number 4. Step number 4, you also have these impedances again between AE and BD, where you have a capacitor divided by 2. So you will then notice we don't have a resistance there. Before we talk about the resistance, so we say the impedance between A and E is the same as the one between B and D. So ZAE equals to ZBD. Because we don't have a resistance, it's going to be 0 minus our JXC. So for our XC, when you look for your XC, then you're saying 1 over 2 pi FC divided by 2, as you see it here. Alternatively, you can just divide that capacitor by 2 and present it as C total. So whichever way, whether you substitute like this or like that, follow your heart. Sharp. So the first 4 steps typically are from given information. All of this is given. They'll give you your line voltage. They'll give you your line voltage. They'll give you VL. They will give you power. Everything here, given data. Given. This is given, yeah. They give you all of this. They give you your inductor. They give you your resistor. They give you your capacitor. So you're not supposed to get any of the first 4 steps wrong, because from step number 4, you're going into dissecting the circuit itself. So make sure you do not get any of these first 4 steps wrong as you approach a calculation. Let's continue. Step number 5, then we're going into the circuit. The intention in this case is to find the sending end voltage and the sending end current. That's why we are going through all of these steps. So next step is to find our current for IC1. The reason why we want this current is because later on we need to find IAB. So by the time you're looking for IAB, because of this junction, IAB is equals to IC1 plus the current going the other direction, IR. So we start first looking for IC1. Let's go. IC1 equals to our VR phase, the voltage just in front of it here, divided by the impedance that current is passing through. So this is VR phase divided by our impedance. We have ZBD. ZBD. Next step. So like I told you, the intention of finding IC1 is so that you can find IAB, where you're saying IC1 plus IR. So you're saying IAB equals to IC1 plus your IR. So the reason you look for IAB is for you to find the voltage drop between A and B. That voltage drop, you're just saying VAB AB equals to the current passing between A and B times the impedance for A and B between these 2 points. Yebo. Then step number 8, sending phase voltage. So for the sending phase voltage, you're saying VAB plus VR. You will add the voltage between this point VAB plus your VR, this VR here. So it's based on voltages in series they add. So you're adding this voltage and the VR this side. So that's how you come across it. So this is going to be VR phase. After finding a sending phase voltage, every time in a three-phase calculation, when you look for the final answer for a voltage, you need to represent it as a line expression. So this is V root 3 times our VS phase. Let's push. So next step, we want to move on to finding IS. The same way you found IA when you said IR plus IC is the same way you find your IS because of this junction here. You're saying IC2 plus IAB. Here's our IAB moving in that direction. So before you find your IS, you still need to find IC2. The similarity with IC2 is the same as IC1. When you found your IC1, you said the voltage in front of it divided by the impedance. For your IC2, the voltage in front of it divided by the impedance. So it's just easier for me to mention it like that. This is going to be VS phase divided by that impedance is ZAE. This one. ZAE. ZAE 11. Then we have IS equals to our IC2 plus IAB. This is based on IC2 plus IAB from this junction here. So that's how we come about that. So we found your VS, the two main things, and IS. Next, the additional things which we need to find: cos theta S. When you look for your cos theta S, you're saying cos theta for the sending voltage plus theta for the sending current. And then they might need you to find the sending end power, root 3 V sending line times I sending times cos theta S. The reason for you to find that is so that you can find efficiency. So this is PS here. So your efficiency is always output over input. Here we have an output. This side we have an input. So based on our symbols, in our case we're saying output receiving end over input sending end times 100%. You may be required, by the way, to find your receiving end power, where they give you maybe S apparent power. So cos theta R, this will be given information. So this is better. There's an alternative formula for efficiency where they say efficiency equals to SR over SS, apparent power at the receiving end over the sending end, times 100%. You can use it. You can use the one for power. Just find PR there and you won't die. Number 15, lastly, percentage regulation. Where you're saying Vs minus Vr over Vr times 100%. So here's your formula. You need to make sure you know how to use it and to use it correctly. So I'm about to do an example in a moment. Sharp. So we want to try to do this question. Let's see. I hope it's clear. Sharp. Let's go through our data. Yeah, question reads, a three-phase transmission line delivers 75 megavolt amps. So, yeah, we know it's a three-phase, and they gave us apparent power. It delivers it at the far end. So everything given here is at the receiving end. This is 75 megavolt amps. Even this VL is at the receiving end. We have 132 kilovolts. Frequency is given to us as 50 hertz with a lagging power factor cos theta 0.8 lagging. It says each conductor has a resistance of 0.25. We're given R. R is given to us as 0.28, so 3 ohms per kilometer. We're given an inductive reactance of 0.63 ohms per kilometer. Then, and a capacitance to neutral of 0.03. C equals to 0.03. This is microfarad. It looks like the capacitor is the only expression given as not per kilometer. We will see in the calculation if that's true or not. Yeah, so let's see. It says use the pi method and calculate the voltage, current, and power factor at the sending end of 100. They gave us a length here of 100 kilometer transmission line. Sure. So what you do with this 100 is its purpose is meant to simplify these values which are measured in per kilometer. So you just multiply that by 100. This is going to be 28 ohms. This times 100, this is going to be 63 ohms. The purpose is to cancel out these kilometer expressions. So 100 kilometers times this, the kilos will cancel out. We're not sure about this capacitor. Maybe later we will see in the calculation. If we happen to see like a very big capacitive reactance, then maybe we may need to multiply it by 100. And we will talk on whether how fair is it that why would we want to multiply times 100, but they didn't mention that our capacitor is per kilometer. So we will talk about it later on. Question says draw the pi method circuit diagram. So it's a requirement always that when you approach this calculation, you need to draw the diagram. So for our diagram, let's draw it here. So we're saying, yeah, so make sure you know your diagram. Labeling wise, it's not a problem. Labeling, there's so many ways of labeling this diagram, but it's still the same because you always have a resistance, inductor, yeah. So here I have VR phase, this side I have VS phase, you have R, XL, this is C over 2, this is C over 2, I have I, C1, I have IC2, I have IS, I have IRA, B, D, and E. Yeah, kizamile sham. Don't judge my nice handwriting and my diagram. Sharp. So to go about this calculation, let's start. So we're calculating sending end voltage, current, and power factor. We're going through the same steps we went through earlier on. So to start, we need to find the V phase. So for V phase, we're saying VL. It's going to be VL divided by root 3. So our VL, they gave us 132 times 10 to the power 3 all over root 3 equals to let's see, what do we have? So 132 times 10 to the power 3 over root 3. We have 76210,236. 76210,236 volts. You represent your VR as 76210,236 at the angle of 0 volts. You can convert it to rectangular form. It's the same value, 236 plus J0. From here, we can then calculate our second step, current. So for current, so maybe before I continue, I'm going to try by all means to convert in all my steps to have a polar form and a rectangular form expression, because when you look at the formulas at the top, you have expressions which are adding across. So when you add, typically we add in rectangular form, you multiply in polar form, or divide in polar form. So that's the main reason. Sections like here, I'm adding in this section. Here I'm multiplying. Yeah, so that's the main purpose of me making sure that I convert certain values to a rectangular form or polar form. We want to find IL. For IL, they gave us apparent power. We have terminal voltage there. We have our receiving end voltage. So it's going to be S over root 3 VL equals 2. They gave us 75 times 10 to the power 6 divided by root 3 times they gave us up here we have 132 times 10 to the power 3. We substitute. Let's see, we have 75 times 10 to the power 6 divided by root 3 times 132 times 10 to the power 3. We have 328,04. 328,04. 328,04 amps. This side, let's find our angle 0,8. Therefore, theta equals to 36,87. So my IR value, I have 328,04 at the angle of minus 36,87 amps. We convert it to rectangular form. In rec, with 328,04 minus 36,87. Let's see. rectangular form, 328,04 minus 36,87. We have this value here. So it's going to be 262,432 minus J 196,824. Done with my IR value. Next, impedance. I have the impedance between A and B, ZAB, which is R plus JXL. My resistance, I found 28 plus J, my reactance 63. I convert to polar form, 28 and 63. So here, pole 28, 63. I have this number. So for my number, I have 68,942 at the angle of 66,038 ohms. Step number 4. Step number 4 is for me to find this impedance between IAE, which is the same as the one at BD. So for that impedance, I need to find XC. So we are about to test what we were talking about earlier on. So for XC, you're saying XC equals to 1 over 2 pi F. This is supposed to be C over 2. Let's test and see our value for the capacitor. 1 over 2 times pi times 50 times. So I told you can find C totals. So I don't recommend that you should do the massive things I'm doing here, where you divide like this in your calculator. This is 2. This is a very big capacitor. Very big. So I'm going to assume there's something very unfair they did to us here. The idea that they did not mention this value, that it's per kilometer here. You know, there's certain arguments. Someone says, you must know. It's not fair, Shem. Because someone else is going to continue with this. Where's that value for the capacitor? This very big number here. So as soon as you come across such values for capacitor, all you do, just because of this thing they didn't do, just multiply this by 100, your capacitor by 100. Consider that even the capacitor as well, it's per kilometer times 100. I'm going to multiply it in there. I'm going to say 1 over, this is 2 pi times frequency times, this is 0, okay, 1 over 2 pi times 50 times 0,03 times 10 to the power minus 6, all divided by 2 times my 100. I've included the 100 just in there. So if that's the case, I'm including it there, times 100 there. 21, we're getting 21, 22,066. 21, 22, 22,066 ohms. So such a case as this one, you saw we tested our answer, we got a very big value for the capacitor at the beginning. So thus we just decided, let's multiply it by the distance. Because you'd continue, later on you'll find currents which are very small, which are unusual in these calculations. So sharp, we want to find the impedance between AE and BD. So we have ZAE is the same as ZBD equals to 0 minus J XC, where we have 0 minus J2122, 066, which is the same as 2122, 066 at the angle of minus 90 ohms. Sharp. Number 5. Number 5. What's happening here? Step number 5, we're going into the circuit AB. This is IAB, AB. Step number 5, find IC1. We're going now. IC1 equals to V R phase divided by Z B and D. Our VR phase we found 76210, 236 at the angle of 0. Here it is. Divide by our ZBD. It's 2122,066 at the angle of minus 90. Then from here we are getting, let's see, 76210,236 divide by 2122,066. We have 35,913. 35,913. 0 minus 90, it's going to be positive 90. We'll convert it to rectangular form. It will give us something like 0. It's going to be 0 plus J 35,913. Step number 6 is to find IAB. IAB, you adding IC1 plus IR. So for our IC1, now what I'm about to do is I won't substitute all these values. I'll add them as you see them here. So I'm going to say I'm adding IR and IC1. I'm adding these values which are in rectangular form, these ones. Those are the values I am adding right now. So to add them, let's go. So I'm saying, let's go 262,432. So when I'm saying I'm adding, I'm saying I'm not writing, the only thing I'm going to write here is the answer in rectangular form, then convert it to polar form. So I'm adding them as you see them, this value by plus. Now for 262,432 plus 0, that number, it's going to be the same number. This is 262,432. I'm now adding the second number, minus 3196, what plus 35. So yeah, all right, minus 196,824 plus, we have a 35. Let's move this, 35,913. We have minus 160,911, minus 160 minus J 160,911. You convert it to polar form. Polar form 262,432 So if you want to write all the steps, I'm encouraging you, please don't trust me, trust your process, or the process, if that's whatever they say. Nah? Let's check if we didn't do anything wrong. Minus 2624,432, yeah, equals to, we are getting 307, 835 at the angle, minus 31, 515, 515, 515. All right, let's see. This is 307, 835 at the angle. This is minus 31, 515 amps. The purpose of this is to help us to find the VAB, where we are saying IAB times ZAB. So if you want, your actual marks are in the final answers for this whole calculation. But we're still encouraging you guys to substitute wherever possible. So here I want to substitute my IAB. My IAB, I found 307, 835 at the angle of minus 31, 515 times my ZAB. I have 68, 942 at the angle of, here it is, ZAB, 66,038. My answer for VAB, 307, 835 times 68,942. I'm getting this massive answer here, 21222,761. This is 21222,761. Yeah, some of these answers, they scare us when we see the minus 31, 515 plus 66,038. This is 34,523 volts. The reason behind all of this is to find VS phase, where you're saying VAB equals VAB plus VR phase, So here, what you then, we did not convert our VAB to rectangular form. So to do that, you're saying 21222, we're converting to rectangular form, shift pole. This is 21222,761. Oh, we don't need it in polar form, it's already in polar form. We need it in rectangular form. So shift rec 1. We have 34,523. Then it gives us this massive answer here. Yeah. We have 17485,406. 12027, 724. So for our values we have 17485 comma, I hope I haven't done any mistake by now, plus J, this is 12027 comma 724. I'm now adding, so to add, I'm adding my VAB, this value. I'm going to add this section. Let me change. I'm adding, let's see, so I'm adding demand O. I'm adding him with this one, those two numbers there. So yeah, this color, I thought it was some math. Yeah, let's see. So it's demand plus demand. So I'll start with the one at the top. I have 76210,236 plus 17485,406. I'm adding the values which are before the J1. Now I'm getting 93,695,642. This is for my VS. So this is 9 yo. All right. So this is 93695 comma 642 plus J. So now I'm saying 0 plus this one here, which is 12027 comma 724. Next, I convert it to polar form. 17485 comma 406 at the angle of 120. Man, I'm calling out wrong numbers. 93695 comma 642 12027 comma 724. Then we are getting this massive answer here, 94464 comma 488 at the angle of 7 comma 315. Next, find VS line. Root 3 times the answer we found, 94464 comma 488. Please confirm on your side if I'm passing or failing. You do that on your calculator. I'm in error, failure. 64 comma 488. Yeah, we're getting 163617 comma 293. You can convert this answer to kilo. In kilo, it's going to be 163 comma 612 kilovolts. And yeah, number 10. Number 10, we are saying this time you're working towards finding IS. You need to find IC2 quickly. To find your IC2, you're saying IC2 equals to the voltage in front of this circuit for AE. So VS phase divided by ZAE. So VS phase divided by ZAE. We have VS phase, we found 94464 comma 488 at the angle of 7 comma 315. ZAE, we have 2122, 066 at the angle of minus 90. Can substitute here 94464,488. I hope I'm writing this correctly. Divide by 2122,066 44,515. 44,515 at the angle of 7, what minus 90. It's going to be 97,315 minus because of the division sign. Kanjalo kanjalo. You know these things. Step number 11, to find our IS. So our IS, we're saying it's going to be these two currents. We're adding IC2 plus IAB. The one going that way, the one going the other direction from this junction here. So you saw IC2 plus IAB. So IC2, we didn't convert our IC2 to rectangular form. Let's convert it here. So it's going to be shift rec for 44,515 at the angle 97, mangma, 518, 315. And then we're getting what? We're getting minus 5,668 and 44,153. So it's minus what? Minus 5,668 at the angle of 44, this is rectangular form, plus J 44,153. So this time you are adding which guys? This time we are adding this one. Where's our IAB? And we're adding it to this one. We're adding those two. So to add them, let's go. So you're saying 262,432 minus 5,668. You're getting 256,764. Saying 256,764. Next, we're adding these two, the J values. For our J values, we have minus 160, minus 160,911 plus, plus 44,153. We're getting 116,758. It's minus J116,758. Convert your final answer to polar form. Polar form. 256,764 for shift minus 116,758. We have 2828 282,064 at the angle of minus 24,453. So we have 282,064 at the angle of minus 24,453 amps. Final step, power factor. Cos theta equals to cos theta S equals to the cos of theta for our voltage plus theta for our current. Cos this is going to be theta for Vs is 7,315 plus 24. You ignore the negative sign. The negative sign just confirms that your voltage and current are lagging. Voltage when the angle is positive is lagging, current when it's negative lagging. So di lagging 7,315 plus 24,453 and oh, I typed the shift. This is cos man. 0,85 0,85 lagging, and then yeah, so what were we looking for? We, my friends, were looking for the power factor. This is such a dark what we were looking for the power factor at the sending end. We were looking for the sending end current, and we were looking for the sending end voltage. Those are the three main things we were looking for. Make sure you know what you're doing. Hola. Yeah, so if there's anything about this calculation is you just need to be careful during a substitution. I don't even know if I got this calculation right. I gave it just down. I don't know. Maybe I'll check the memo, Shem. I'll check the memo, but it looks right to me. You guys will confirm. So if there's anything we were talking about, we need to be careful about our substitution. Also, just to come back to what we noticed earlier on related to the capacitor, they didn't specify the microfarads per kilometer. Maybe someone else can justify it better than me, but during the calculation we noticed our capacitive reactance was a very big value, and so I just know we were going to get it wrong. But yeah, so just try to make sense out of these values as well. Also avoid writing maybe your phase voltage as kilovolts or your current in kiloamps. You might risk forgetting later to convert it back to amps or volts. Then it causes you to get your calculation right. So yeah, sharp.